Cloud. So good afternoon, everyone. I hope everyone is well, even with some COVID restrictions in some of the countries that you are participating from. A very warm welcome to all of you, and thanks for showing interest into Arise. So there's many people that already know Arise, but I also see very many new names from different organizations. So big welcome to you. And let's start then with a little bit of an introduction to Arise, because I don't know if everyone has seen us before, but also to give you a full overview of this very interesting year for Arise. So that will be about 5 minutes, then you get an update per team, and then we have the breakout room. So I really encourage all of you to join us for an open discussion after the presentations, because I think that's where the fun and magic really happens. So Arise, I think without too much ado, we all know that there's a big biodiversity crisis happening right now. And this is the main reason why Arise is actually happening. So we got this funding. Why? Because biodiversity is a key function to our planet and our own human survival. Yet we don't know which species that make up biodiversity actually exist. Many of these are not visible. Many of them have not been discovered. So it's really essential that we capture biodiversity by starting with species identification. So that's our first kind of big vision, identification of any species on any level in any environment. So really increasing our knowledge and technology to do these kind of species recognitions. But also to facilitate biodiversity research. So of course, recognizing a species is just a starting point. But if you recognize species in co-occurrence, you really start making these networks of species and who's dependent on who and what's really going on. So it's also connecting data just beyond the species identification. And then if we are really doing that, you can also start monitoring biodiversity. So what happens in time or with given seasons or under particular conditions, and really start answering ecological questions. So if you take all of this and you push it into Arise, there's actually 3 big pillars that we work on. On the one hand, it's really high throughput sampling and sequencing. So we know this takes a lot of time and effort. So really going into the field, collecting material, discovering what it is, and we really want to make this as simple as easy that it can get to, but also cheaply. This is for a single species, but also for multiple species or even environmental samples. So not even going into which are actually present, but what's in this bag of soil or in this piece of water to get an indication of what kind of species are around. This requires standardized and automatic processes. So we will be involving all kinds of tools, robotics, wherever we can. There also needs to be a transparent tracking and tracing so that we know exactly where the data comes from as soon as it's captured in the field or even before it's in the field. And all of this needs to be done rapidly and cheaply so that it really becomes accessible for anyone who wants to do this type of work. There's a huge digital component to Arise. You can imagine there's already tons of data available, all kinds of species information or observations out in the field from different organizations, but it's all quite scattered. And what we want to achieve with Arise is to allow that data to communicate to each other. So we don't want to harness all the data. We don't want to collect all the data because we can't do everything ourselves, but we want to build the infrastructure that can at least have data communicate to each other. So that means that we need to facilitate digital input, not just barcoding, but also other types of information that could help identify a species. So radar, sound, images, and maybe something else in the future. It also means that we need real-time identification, meaning that we have AI models running, but also want to allow others to build AI models to help us identify species based on the given input. All of that, of course, needs a platform. You can't just have a tool here and there. There's plenty of tools around, but we also want to create this platform where you can go to and find the necessary information or the necessary tools to do your work on species identification or biodiversity research. And making the circle round, we also really want to innovate on biodiversity monitoring. Why? Well, we know it's a lot of effort to identify species, even if you have pictures. So how can we actually do that faster? That's also by looking into devices. So we know, of course, there's no way that we can replace a human. There's a lot of knowledge that a machine doesn't have. But if we know how to replace part of what a human can do, we can do it 24/7, all year round with these devices. And that will give us a lot more information to do something in the field about biodiversity. So for instance, change our policy around a given species or multiple species or ecosystems. How do we work in Arise? Well, it's a growing team, I would say. We have now 5 teams working on some of these core pillars within Arise. You'll get presentations of all 5 of them. They're dedicated teams, mostly. They're multidisciplinary teams, meaning that software engineers can sit together with lab technicians, can sit together with researchers, ensuring that actually that diversity leads to better services or better outcomes, because we all think a little different and we bring some different knowledge to the table, but collectively, we actually find the best solution. We will build on existing knowledge. We have, there is already a lot of data. There are already a lot of tools that we know of. So we love to combine those, love to further develop those to really build something strong. We believe in working iteratively. So we won't go into a, hide and seek hole for 5 years and then suddenly come up with a perfect solution. We actually believe that we need to focus on particular end user value or so-called user stories and build them iteratively. That's also why we have this town hall every 3 months, every quarter, to show you what we've been up to and really ask for your feedback on this. These are the people, and you'll hear more about them right now. So Hanko, over to you.
So good afternoon, everyone. My name is Hanko. I'm the team lead for sampling, and we have 2 big goals. If you can go to the next slide, to facilitate the vision and mission of Arise, which is building the reference database, because without this reference database, we can just try to do whatever we like, but we don't have the basis. And the other goal is to optimize all the processes that we have from in the field sampling up to the lab and into the collection. We've been working the last few months, if you can go to the next, on defining how the specimen collection for this reference collection should look like. It defines what we will store, how long and how. And with the definition of how we define it now, it gives us a lot of opportunities to test storage methodology and equipment, which is really nice. So you can take a look at the traditional storage methodologies, which exist for hundreds of years, if it still works optimally like we do with the knowledge now. And besides looking at this, we also worked a lot on the collection mining Braconidae. We checked hundreds of drawers from the collection, because I think the collection holds a lot of value, and we should start there. And actually, we found that almost 83% of the species can be found already in the collection. They have been selected already, and the next steps are photography and subsampling for DNA, which we just started like a week ago. So the estimations here, the selection process takes about 2.5 minutes per specimen. This also takes the time for getting the drawers, taking them from 10 floors down to the lab. So it also involves a lot of transport logistics. The photography takes a lot of time and subsampling as well, but this is just because we just started. So we have only 6 hours in here. So this also involves finding out the methodology, how we have to work and everything else. And eventually we will have photos like on the right side of all the specimens, and then we can subsample. And we choose for this format because the photos have really high quality. And if you go to the next slide, you can see that you can really zoom in onto the specimen and see rather a lot of detail. So this is a trade-off between stacking and just a very quick snapshot photo, which we think it has enough quality for the ongoing process. Yeah, and also besides checking the collection, we receive hundreds of specimens from collectors in the Netherlands. We've received several batches of hundreds of marine specimens, a large number of beetles, parasitic wasps, and these have also already been processed and are ready for gene sequencing to get started with the sequencing processes. So on the right, you see a lot of photos that we make just for in a process to keep track of all the specimens and have built this reference database. Okay, yes. So for the next year, we continue to finish the Proconidae collection mining pilot for all the subsampling and photography. We will start a DIOPSIS comparison pilot. So this is a pilot to compare the DIOPSIS cameras with traditional sampling in the field to see and test how good DIOPSIS cameras really are. We will start building a prototype for the sampling tool, which probably should make it easier to translate metadata to all the systems that we have. And also next year, early next year, we will start hiring 2 sample managers and start with several students. So that's about it, I think, for sampling.
Cool, many thanks, Hanko. So moving on to sequencing to really make that high throughput sampling and sequencing happening.
Yeah.
Kevin, all yours.
Yeah, just a short recap on what sequencing team is doing. So we are involved in every step in the process, from the DNA extraction, once we get specimens from Hanko and his people, to the clean sequence data after bioinformatic analysis. And the main goals are more or less to reduce costs and make everything high throughput with a whole bunch of automation in there. And all this to sort of uncover 95% of genetic diversity of multicellular life in the Netherlands as our goal. So yeah, we've been working on that for a couple of months now. If you could next slide. We had several pilot projects. One of them involves meta barcoding, so we'll get back to the barcoding stuff later on. But first, we want to show some meta barcoding results from soil samples, fresh out of the oven. I just ran these graphs yesterday in R. Because part of this pilot was to see if we set out a grid in an area, how many samples do we need to take to uncover the full diversity of this area. And as you can see from the graphs representing the raw data, that even after 95 samples, it's still a growing line. So it means there's a lot of diversity, albeit some of it's very rare. But it shows that just taking 1 or 2 samples in such an area is probably not enough. So we need to fine tune this a bit more. Of course, we also need to still look at the identifications of all this DNA. We have some wonderful reference databases already at Westerdijk Institute, which we need to compare our results to, but also check against some of the cultured fungi. On the next slide, you can see some of those cultures. There's beautiful pictures. I mean, beautiful in the lab, probably not if they're in your bathroom. The fungi barcoding is going at full speed. We're about to hit the 2000 specimen mark. So we have lots and lots of reference sequences from the collection, from Westerdijk, but also a lot of samples that have been cultured from the soil samples in the metabarcoding pilots. For the DNA barcoding process, 3 months ago, I told a bit about how we want to sort of reduce the costs, and we've started optimizing our protocols now. We finally got our homemade DNA extraction protocol to work by adding some extra washing step. That seems to be doing the trick. And as you can see from this graph I show in this slide, in the red dots represent the 3 plates we did now. About a 76% success rate for the DNA extraction and PCR. These are samples from Malaise traps we got. So I thought it was an interesting idea to set it out against the success rate of dipterans, hymenopterans, and small lepidopterans. So sort of stuff you get into Malaise traps from the past decade. And there we see that it's well within the range of those plates that we're still using the expensive Git protocols. So the success rate is about 76% versus 82% for the previous extractions, but at 6% of the cost. So that's quite a reduction. And we're actually now in the stage for the DNA extraction that the majority of the costs for DNA extraction now is plastics. So the next step next year will be to also try and get rid of those plastics as much as possible. Then the other big hurdle we had to take was the sequencing. Sanger sequencing for barcoding is nice, but it's really expensive. So we've been trying to get it to work on the nanopore, third generation sequencing as is. And it actually worked last week or this week. So it's a nice way to finish off the year and start the holidays with a smile on our face. And the next step is to further optimize this process to get more and more samples into a single run to drive down the costs even more. And then the next slide. Yeah, so of course, this is nice. We have raw data, but then the raw data needs to be transformed into actual barcodes. So we have a reference database. And we've now designed the first sort of pipeline, which will be built in the next couple of weeks. So we can have our first prototype up and running, see what needs to be tweaked. And now that we have our data too, it will be a bit easier to test the pipeline. So hopefully that will go smoothly. And then, yeah, like I said, we're working on reducing the plastic waste. So we already bought 2 machines, or we have the okay to buy 2 machines to reduce the plastic. Yeah, you can go back to. And then for next year, yeah, lots of other optimization. So hopefully we'll finally get a LIMS up and running, some nice robots, maybe not as fancy as the one in this picture here, but still good to have some processes automated nonetheless. And then we can also start optimizing the rest of the workflow, mostly the PCRs, which are now the most expensive step next to the plastics. And we will welcome our last technician. So the team is now complete, and I just saw he's in here, so hi. And then, of course, we have all the material that Hanko is collecting, so we finally can start working towards the operationalization. That's it.
Fantastic. Thank you, Kevin. Yeah, so like I mentioned, fast, cheap, accessible, but of course that's also so that we can go towards 100% of all species in the Netherlands being identifiable, at least also with a barcode if possible. So awesome work. Thanks a lot. All right, moving over from manual actually to the other side of the team, the monitoring demonstration sites team. So welcome, Daniel.
Yes, thanks, Elaine. My name is Daniel Kissling. I'm from the University of Amsterdam and leading the team on the monitoring demonstration sites together with Rotem Silver. She's the assistant project manager and also responsible for the connection with the sites and the running of the equipment in the field. I would like to acknowledge also from the year that we had a number of people. I had the names originally on there, but I removed it for privacy issues. But I would like to acknowledge a number of colleagues from UvA, both within our institute and the technology center. We had worked with a number of people from Wageningen University, Wildlife Monitoring Solutions, FaunaBit and Naturalis in the connection with the sensors that I'm showing in a moment. But we also had great collaborations with monitoring stakeholders at particular sites. So for instance, from Artis, Staatsbosbeheer, Waternet and the Flevolands Agraris Collective. And finally, also good connection now to SurfSAR for the data storage. So yeah, please. So the main aims for the monitoring demonstration sites are on the one hand to establish sites for monitoring demonstration and test multiple sensors at those sites. And those sensors are mostly focused on automatically detecting species and collecting the evidence of the occurrence of species. As a second point, we have really our aim to demonstrate the innovation potential, and at the same time collect and develop knowledge and experience with a range of different automated monitoring devices that can go for image, sound, radar. And we also want to deploy them in different environments, not only different from an ecological point of view, but also the challenges in different types of habitats to run and maintain these equipments. And then finally, we want to connect to scientific users, monitoring stakeholders, and the public. So we had in this year focused as a start on a number of pilot sites. First of all, in Amsterdam, Artis Zoo. That is a great site on the one hand for us because it's close to our university, but on the other hand, it's also a great site for public outreach. Artis Zoo is very interested in showing to the public the potential of automated monitoring systems. It's also interesting for studying urban biodiversity. We have worked at the Amsterdamse Waterleidingduinen, a tune ecosystem. It's a relatively remote location, so quite a number of challenges with data, automated data transfer, and it has grazing exclosures, which makes it interesting from the ecological point of view. We had an agricultural site in Flevoland, studying from the field margins to the crop center, interesting for farmland biodiversity. And then we also started to work at Oostvaardersplassen, a very interesting rewilding and restoration site with wetlands, grasslands, and as you probably know, the large herbivores that make this. Yes, so here's an example of the deployed sensors that we had in this year. On the one hand, on the top row, you see, for instance, wildlife camera traps. You see in the middle an acoustic logger, and then on the right hand, a radar system. And in the bottom row, you see a number of different insect cameras. Most of all, we have worked with DIOPSIS, but we also tried out, on the one hand, a Moth trap camera and a more intelligent camera that has a GPU computer already on board. I want to show a few examples. So, for instance, what you see here in the picture on the left is two Sniper Commander 4G wireless wildlife cameras. They allow to, on the one hand, to be run on solar panel in the field. On the other hand, they are 4G, so that means we can transfer the data directly. We don't have to collect memory cards. We have set up a number of them, I think a total of roughly 30, 35. Some are still to be installed across Amsterdamse Waterleidingduinen, Artis, in some gardens, and Oostvaardersplassen. And we have also set up a number of other cameras, these Browning Spec Ops wildlife cameras, which we put in a public space in Flevo Park, where we cannot run it with solar panels and the 4G data transfer because it's too obvious, those cameras. So we're also testing different options. We have collected a range of images. So each of these cameras typically takes 5 images triggered by an infrared sensor once an animal passes by. And we had more than 55,000 images already collected and 16 to 17 gigabyte. What you see in the center is an example of some images collected at Amsterdamse Waterleidingduinen, where the rabbits are particularly often detected, the yellow one. Next example are, for instance, the audio Moth. We have set up a few of them at Artis, at Flevo Park, and at Oostvaardersplassen. We're going to install them. They allow to collect continuously audible and ultrasonic frequencies. So, for instance, for detecting bird songs or squeezing of rats or even insects. We have, those are relatively low-cost devices with micro SD cards, so we have to collect them. And we have at this point about 7 terabyte of data that were collected in the last few months. The next example is the radar. These are really expensive devices. We have one radar, one of these bird radars at Artis installed. It's very interesting because that allows you to detect moving objects like birds, but also insects, so mass migrations. These radar run continuously. And we have also set up a Shiny app that you can see with the QR code on the bottom. And if you click on, or if you scan this in, you get to a live demonstration of what has been passing by in Amsterdam in terms of birds and insects in the last weeks. So this is huge data. We have just in the last few months more than 30 terabytes of data from that scan radar. Another example we've worked a lot is the DIOPSIS insect cameras. We have established them also at a number of sites, Artis, Amsterdamse Waterleiding down of Flevoland, Oostvaardersplassen. And that is an interesting system because it on the one hand allows you to collect images on a regular time period, both on day and during night, so both night active insects and day active insects. And the data are directly uploaded by 4G to a server. And because of the regular timing and collection, that are hundreds of thousands of images and huge amounts of data as well. So for all these devices, it's not only to get the experience with setting those up, but also to understand and set up and learning about how these data streams are actually working. So on top, you see an example from the Sniper Commander 4G camera, which transfers the data via 4G. We have set up together with Wageningen University at this point an FTP server where we can store the images before we transfer them to Agouti. This is a system that exists that allows the annotation and species identification developed by Wageningen. And then finally get in the CSV output with in a standardized format that uses a metadata standard for describing the data. Below you see an example that we have set up for the audio Moth. So there we have to collect the SD cards, and we have established a data archive at Surfsara where we can upload those files. And at the moment we work on, or one of our colleagues at UFA works at identifying rats through a deep learning methodology called DeepSqueak, and that also comes in with a CSV data output. Two other examples: the radar is a relatively advanced system. We have a data transfer with a wired network at Artis, and that goes then directly to a cloud server, to a relational database in the cloud, hosted by a Swiss bird radar, and from there you can then access it again. And we have established a Surfsara data archive, in this case the research drive, that allows to store the signatures, databases, PNG files, and the process data packages. And this is all research done by my colleague Judy Chamon-Baranes. And then finally, for the DIOPSIS, we have a 4G data transfer at the moment. This goes first of all to Phonabits and Amazon servers that are installed, but then we also move it to the Naturalis servers and work both on the data storage and the species identification. And that links what you hear later about to the DSI team of ARISE. Maybe one other aspect was the public outreach, and their Artis is for us very relevant. We had from overall ARISE participated in the Amsterdam Gemeente Academische Tafel. So it was a bigger event inviting many stakeholders across Amsterdam, and ARISE was presented there. And we have also a number of equipment in Artis, and there is the first plaques also there that describe the equipment and introduces ARISE as an infrastructure. On the left-hand picture, you see Judy presenting the radar that you see in the left back to a number of people there. Yes, thanks. So the outlook for 2022, we have collected the first experiences from this year. So we will have to redefine or refine our existing monitoring sites and expand them. We have, for instance, not covered so far aquatic ecosystem forests. We have relatively little in agriculture areas. We are also working together with the team from Jakob, who's talking in a moment, and the University of Twente at a living innovation lab site, where they are creating a site that allows to calibrate and test new technological solutions for infrastructure and sensors, and that's where we are going to contribute with ARISE. We also want to test a number of other sensors. So far, we have very much focused on the terrestrial sensors. We also want to expand it to aquatic sensors. We want to go to more smart acoustic devices, so that we have automated monitoring units. For acoustic devices, it's a bit challenging because you have large data audio files. It makes the data transfer more challenging. We look into Nestbox cameras, phenocams, weather station. We also want to look into GPS tagging for tracking animal movement and other things. And then finally, We have also discussed and started a number of technological innovations that we want to look at. For instance, how we can set up a wireless mesh network with a number of sensors that are connected, for instance, to a base station. And we're going to test or develop that for an example in the Veluwe National Park. And we are also discussing, for instance, with Amod, how we could develop stations that have multiple sensors incorporated in one system, or on the other hand, how you can combine information from multiple sensors and basically a multi-sensor data integration. We have for our end, together with the Biocloud team, data scientists starting Julian Evans in January, that will help then also more with the data science. That's basically the overview from the monitoring demonstration sites.
Excellent. Thank you, Daniel, for the extensive input. So move on to digital species identification, another missing piece in this cycle. Jacob.
Yes, good afternoon. I'm Jacob Kamminga, and I work at the University of Twente with an awesome team that we call the DSI team. And I'll tell you a little bit about what we have been doing so far. So you have seen this slide at the beginning, and Patrick Janssen pointed out it's actually the wrong name apparently. So let me tell you, this is not an actual output of DSI yet, just an example to see what we want to achieve. And on the next slide, I have a few more examples. So what we are trying to do is build an infrastructure that can be used to develop algorithms that identify species in images, but also in sound and radar data. And obviously, it's to do it better than we did in this presentation. Yeah, and not just sound and images, but also for each project, we want to host a variety of different use cases. So for example, insect detection for DIOPSIS, but also counting animals, yeah, and be able to support a large variety of different projects. So in order to do this, we came up with a design with a large variety of modules. If you want to know more about those, please join the breakout session. For now, I'll tell you what where we started. That's actually at the end of this list, an algorithm repository and deployment of existing algorithms. So with this algorithm repository, we want to host various algorithms that may cover the large variety in use cases, so different geographic regions, media types, taxa, etc. We want to provide versioning and provenance to really speed up development and make it easy to share and maintain. And we want to allow users, different users, ecologists, but also algorithm developers to select algorithms, either to deploy for DSI tasks, to analyze data, but also to use as a pre-trained model for new algorithm development. And we also want to allow developers outside the RISE to propose algorithms to publish in this library and to share, because we need a lot of them. So what we envision is an algorithm browser where you can actually look for specific algorithms that may be suitable for your project. So you can start there. So here, for example, I list 3 different versions of DIOPSIS. For DIOPSIS, that's where we started, the insect cameras. And in the next slide, we also imagine that you can compare these algorithms to help you choose for data analysis or for algorithm construction. So the idea is that you first look for an algorithm, and that it should be easy to select an algorithm and very easy to deploy it. So this arrow, in this case, moves an algorithm to a deployment situation. This green arrow is actually a lot of work. This is a continuous integration, continuous development pipeline, which we are currently setting up. And once an algorithm is deployed, of course, you want to start using it. So that's the next slide, where you need to send images to your algorithm and you need to store the analysis results. And in this case, we, like I said, start with the DIOPSIS workflow. And at the same time, on the next slide, we are also working on a soundbird classifier. So instead of sending images, we are sending audio files to a bird sound classifier. And Dan was working with a student, Alberto, and our developer, Patrick, recently, and got this actually working. And of course, we are And next year we will continue integrating this into our pipeline. And we're doing this simultaneously with DIOPSIS to make sure that what we are developing is generic, and we don't focus too specific on one project. So in the next 3 slides, I'll show you the workflow of how to use this repository and algorithm deployment. So if you're an algorithm expert, you want to browse algorithms, select an algorithm, and want to easily submit it to a deploy service. In this case, we use Docker containers. And once the algorithm is deployed, on the other hand, we have an ecologist who wants to analyze a set of images. So in this case, this is from DIOPSIS. So we have a camera that's uploading images to the Biocloud where it's stored. Oh, sorry, Elaine. And the ecologist wants to find a set of images. In this case, as an example, cameras from Artis from June to August. And after investigating these images, creates a data set. And the data set can then be stored in the Biocloud. And then the ecologist says, okay, I want to analyze this data set. So we built a service which combines these 2 aspects, the data set and a deployed algorithm, which we have coined the analysis job runner, which runs the data set against an algorithm. And then the results, again, are stored in the Biocloud. And once you have stored the results, I didn't put it in the slide, but you could use these to generate a report. So that's very, very quick on the workflow we have built. We have built this. This is actually running as a prototype, and we are iterating on this. If you want to know more, please join the breakout session. Some other exciting news. SURF has joined this meeting, and we are talking to SURF about compute services. And we actually may join the Dutch National Supercomputer, which is really good news because that means we can train very big algorithms very fast. So I wanted to share that with you as an exciting news, but nothing set in stone yet, but we are talking to SURF about this. And yeah, I forgot to put out, I deleted one slide for next year, but yeah, I think if you want to know what we will work on next year, please join the breakout session.
You're more than welcome to name a few, Jacob.
Yeah, so okay, we will work on the other modules. I tried to paste in the slides, but it doesn't work apparently to update it. But next year we'll work on AI construction and training, AI evaluation, and comparison, also at some point annotation, because it's integrated with the construction and training of algorithms, and actually deploying it in the cloud as well as a web service. So a lot of things to do.
Yeah, so the idea is not just choosing AI algorithm from the library and using it to analyze your data, right? But also allow people to annotate their own images and potentially even build their own AI model, right?
Yeah, so the full pipeline indeed from raw data to algorithm training.
Fantastic. Thanks so much, Jacob. So gluing all of this work together, because there's many aspects to Arise, as you noticed, is the Biocloud team.
Thanks, Elaine. Yeah, Biocloud. I often refer to our team as building the iceberg, of which most of it is underwater, and what you will see is just a small top. But I guess you can imagine from the previous updates from the team leads, there's a lot of data being collected, and the Biocloud team is actually trying to make sure that we can store, manage, access that data in a fair way, which is findable, accessible, interoperable, and reusable. So I've shown this image before if you've joined Townhalls before, but just as I guess a repeat of what we're trying to do. The Biocloud team is both developing the underlying infrastructure for Arise, as well as providing an interactive platform where people can access data and services. So the top green layer that you see here is the top of the iceberg. That's what will be above water eventually. A one-stop shop, as we often refer to it, where you can access data, where you can access the algorithm repository that Jacob just mentioned. We are also aiming to develop an annotation workbench where the human in the loops can actually annotate data that is collected, and a storage portal. But to actually get to a platform, there's a lot of work that needs to happen first to actually develop all the backend facilities and services to allow good access and management of that data. So that's what the Biocloud team is mostly working on at the moment. It's all about data management and storage and designing a good way of storing this data as digital objects, as fair digital objects with persistent identifiers so that people can find them now, but also in the future. What is also important to us is that we do think about access control. So if you upload your own data, you can also have some control about who's able to access that data, even though we are focusing on being an open source platform and making data openly available. We're also really focused on linking to already existing systems and other data infrastructures, because a lot of the data that we are aiming to provide access to is not just collected by Arise, but is already available in other systems. So next slide, Elaine. So Jacob already showed a bit of this Biocloud in one box in his workflow diagrams. I'm trying to make it not such like a black box thing, although most of the end users of Arise will not really need to understand how the Biocloud works from the inside. But if you've heard me speaking about Biocloud before, you might know that we are using two main components, Cordra and iRods, to build the Biocloud. These are software tools to store both metadata and files. So iRods is a virtual file system that you can link to a lot of different storage options. So whether your data is stored at Surf itself, in active storage or in archival storage, or at Amazon S3 or elsewhere, iRods is the man in front of the storage system. We refer now to him as the SureGuard man, who actually can orchestrate where data can be stored. So based on access time or particular metadata, we can also move data to cheaper long-term archival storage if needed. We work together with Surf on implementing this. They host iRods as a service. So this at least helps us with focusing on how to implement it for Arise rather than all the nitty-gritty details. Cordra is developed by CNRI in the US, and that's where what we use for storing metadata and assigning these identifiers for the different digital objects. What you see in this schema is the design of the prototype for Biocloud. So the images come in from a camera into the Biocloud, where we store the metadata in Cordra and the actual file in iRods. We are building a query service where you can define a query, say, I want to find all the images from this camera on this date. And that Elasticsearch will then generate a data set of IDs, so of identifiers of the digital objects, through which we retrieve the actual images linked to those IDs from iRods. And that data set will then be sent to the DSI algorithm, and the results will also be stored back in Biocloud. There will be a whole platform also built underneath this where you can actually access that data. If you do a click, so the main work that's going on right now is building APIs for indexing and storing this data, configuring iRods and Cordra, doing a lot of performance tests, because it's all well and good when you can put two images in the system, but I think DIOPSIS last season collected 10 million images, so it needs to be relatively fast as well if you want to retrieve data. We're testing and fine-tuning and testing and fine-tuning. We hope to have the prototype of this of the Biocloud ready relatively soon. Then the next slide. So while we are working hard to build the underneath the water iceberg, we also have people who are already starting to think about what this should look like for an end user. User experience and design is a very important component in developing a big program like this, because if we want a platform that people actually will use, then it needs to be user-friendly. And we're really focused on iterative design. So we'll start with a prototype, ask potential users what they think of it, and really work with them so that we build something for the end user rather than how we think it should look like. So we're very lucky to have two UI UX students working with us on a prototype, and they've been testing this with people who have been using the DIOPSIS cameras in the field, so they know how to deal with this data, what they're missing. So Elaine, if you want to click on the next slide. These are just some screenshots of what they've showed us last week. They've been testing this with actually making people click through the prototype and asking them questions about how they like the look and feel of it, if it already has the functionality that they are expecting. And it's really, really cool to see them. They'll probably stay on for another half year, so we're very excited to bring this further. And then the last slide, I think. So while we are working on this first workflow for the DIOPSIS insect images, as Jacob said, we're trying to build everything as generic as possible, because there's more workflows that we have to account for. So we are already working a lot with the sequencing team. While they are developing their workflow for the DNA data, we want to make sure that we can also store and manage that data in Quadra and iRods when we get there. Together with the UvA, we're generating ideas about how we can integrate their radar data in our system. And there is already a Dutch species register, and we're thinking about how we can extend that and expand that to become the Dutch the species reference database for rice. We can still use some more software developers in our team. So if you do know someone with technical skills and a passion for nature, please send them our way. And I think that's it for our team.
Yeah, thanks, Chantal. That's super awesome. So I know that you've noticed probably that we're mentioning DIOPSIS a lot. That's not because we're just working on a particular camera, but we've been using this, as I said, our use cases, so that we can really focus on one case, build that end to end. And by doing so, we know all the aspects and then can copy paste that to actually other use cases and devices much more easily, which is a practice that has been, well, coming from our agile way of working. So I'll keep it short. What else is happening? We're fully operational. Like I mentioned, a year ago, of course, we didn't really exist, but now over summer, we've really started to form teams, have a common work style in Agile. Almost all vacancies are filled. And of course, we're missing a few people, but we're really getting beefed up, so to say, to do the actual work. We've been in the picture, like already mentioned, in Artis, but also various blogs are being presented so that we also get our news out there. The Townhall of last time was viewed on YouTube 188 times. So that means that people are actually watching what we're doing. And so are you here today. 85 people listening to us. That's pretty cool. So I hope that we keep you interested and you keep approaching us with your feedback. Our website is improved, so have a look. And we also connecting to other infrastructures outside of the Netherlands to learn and share knowledge, because some of them are already up and running, some of them are developing as we speak. So it's very interesting to learn from each other, what goes well, what doesn't. And so now we've connected to AMOT in Germany, and we will soon reach out to SPDI in Sweden and yeah, kind of build our network from there. 2022 is going to be interesting, so I hope you stay tuned. We officially started last year, September, but the first few months were a bit slow, lots of administration. So we're actually really operational for a year now, with lots of hurdles. But like I said, big teams now forming. So we're really, the steam engine is getting up to speed. So I really feel like a lot of things are happening next year. Do keep one date already in mind. I'll send an invite to all of you already. The 30th of March, we're planning to do an Arise Day, and it will coincide with a hackathon to really kind of build this community around Arise and get more feedback, more input, and people being aware and build the network. So I hope, you saved that date for us. Thanks for listening. I will stop the recording here. Don't go away because the breakout sessions will start soon. So hang on. That was it for the recording.